I like the term active shooter too, like he's going to be like.
Just jogging.
Yeah. For today's active lifestyle. Yeah, wearing like leg warmers and a poofy headband. Let's get physical. Okay, so exam 2 is a week from Thursday. So that is the 13th. And the topics for that we'll be conservative with this. So first, it's cumulative, and so that's important. You got to make sure that you understand the old stuff. There'll be questions on old stuff, and then the last one didn't have particle statics on it, right? So particle statics. Oh, okay, we didn't have, right. Okay, so rigid body, free body diagrams, did we have that?
Yeah, we have that.
Okay.
Just rigid body statics.
Okay, so all we're going to do is rigid body statics. That's the only new stuff. But that's a lot of stuff, you know, that's important.
So that includes 2D and 3D.
That's 3D or
2D and 3D, yep, all of those problems. But you have over a week to solidify this stuff.
yeah.
And so today, all I'm going to do is I'm going to finish the example problem we did and do a couple more example problems. And then briefly I'll cower in the corner and then go back to example problems. Okay?
Last question about like the homework.
I'm going to try to pee myself to make it more realistic, but you're going to have to look away because I'm bashful. Yeah, exactly. You can't look at me while I'm trying to do it.
For our examples, can we request examples from our homework?
Yes.
Okay.
Unless due Thursday, right?
What?
Homework? Due Thursday?
Homework is due Thursday, and I'm not going to assign anything new today, so it's just those rigid body problems. Well, and whatever I said before that. Whatever, you know. No new stuff for today. That's what I mean. Any questions about the test? Okay, so last time we were in the middle of this problem. So let me just remind you what's going on here. There's a ball and socket joint connecting this rectangular shape to the wall. And then that ball and socket joint would let this flop down. And so that's prevented by a cable here going over to A on the wall and a cable here going over to B on the wall. And the dimensions are given. They're not really drawn to scale, but the dimensions are given. And so a free body diagram looks like this. And the way to think about that is first apply the weight. And then up here at the ball and socket joint, a ball and socket joint always applies an unknown force vector. And then there are two cables, and so those are forces with known directions. They're parallel to the cable, away from the chosen body. And let's see, we chose the origin to be at the same place as the about point at that ball and socket joint. And one thing to notice, I'm filling out this table with the P and the A in it. Anytime you choose your about point and your coordinate system to be the same,
that means that your about point is 0, which means P and A are sort of unnecessary. P just matches rho. So when you do it like this, you can just as easily skip these two columns. Okay? And I think that's a slightly quicker way to do it. Just put your about point and your origin at the same place, and then all you're doing is, rho is the location of that force. Okay, but I'm already doing it this way, so let's keep doing this. We already did the force at the ball and socket joint. We already did the weight force. Now we are doing the force TA. And we did that by calculating a unit vector that points from C to A, and then multiplying it by the force TA. So I'll enter that in here. That's negative 0.816 TA. And then 0.408 TA, 0.408 TA. And then the cross product, we have 0 and then negative 0.816 TA, and then positive 0.816 TA. Any questions about that one? Did I jump back into this too fast before you got your bearings? Yeah.
If you can just further explain, I know you're going down with the criteria from left to right, but
Yeah.
going down
The table?
yes.
Okay, yeah. So each one of these rows is one of the forces on here. So this one is this is that force R. This is the weight. This is the cable force TA. Now we're going to have one for that cable force TB. Sure. That force TB is that's acting at 2.500. Our about point is the origin, and so this is what I was saying. You can skip the step of writing these two things, and the rho vector is just equal to the coordinates where the force is applied if your about point and your origin are the same. And then it looks like I already did this one too. So that so we calculated a unit vector going to B from D, and then multiplied it by the force TB. So negative 0.707 TB uh, 0.424 TB and negative 0.566 TB. And then if you take that cross product, you get 0, 1.42 TB, 1.06 TB, Cortland, don't freak out, but there's going to be an active shooter drill at 10. It's not real. Okay. Just want to make sure we're all on the same page. Okay, so now we're going to take all these forces add them up and use them in Newton's second law. Then we're going to add up all these forces, add them up in the rotational equation. So Newton's second law looks like this. What did I call that force? Just R? Rx, Ry, Rz plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 0.707 TB, positive 0.424 TB, negative 0.566 TB, plus 0, negative 490.50. So that's adding up all the forces. We just went right down this column, added them all up, and then set it equal to 0 because it's in static equilibrium. This over here would be the MA if you were doing dynamics. And then the moment equation says 0, negative 0.816 TA, positive 0.816 TA, plus 0, 1.42 TB. I'm going to let the rest of the people just freak out when it happens. I'm not telling anyone else. 1.06 TB. Plus 0, negative 613.13 is equal to zeros. Okay, so now let's look at this system of equations. In general, when we have a 3D rigid body problem, we're going to have 6 equations for 6 variables. Something comes up pretty often in these that doesn't come up in 2D, and that is a lot of times some of these, one or more of these equations are degenerate. So this one right here just says 0 equals 0. So what we really have is now 5 good equations for 5 variables. And so in 2D, you're used to just counting up the variables, saying we know we're going to have 3 equations, we have 3 variables, it should count. Here, a lot of times, you're going to have fewer than 6 variables. That'll still work as long as you have fewer than 6 good equations. Okay. Well, let's just write out this table. Okay, so we have a system of 5 equations for 5 variables. So there's equation 1, 2, 3, 4, 5. Here's variable 1, 2, 3, 4, 5, and then this is the constant. And the variables, I'll go the first 3, Rx, Ry, Rz, and then Ta and Tb. So Rx, Ry, Rz, TA, TB. The first equation says RXs we have 1, TAs we have negative 0.816, TBs we have negative 0.707, and no constants. The next equation says okay, RYs we have 1. TAs we have 0.408. TBs we have 0.424. And the constant is going to be positive 490.5. Okay, so RY we have 1. TA we have, was it 0.408? TB we have 0.424. And the constant was 490.5. Then the third equation, RZs we have 1, TA 0.408, TB negative 0.566. So 1, 0.408, negative 0.566, and the constant is 0. The useful equation number 4 now is this y equation for the moments. So TAs we have negative 0.816. TBs we have 1.42. No constant. And then the fifth equation, TAs we have positive 0.816. TBs we have 1.06. And the constant, when you move it to the other side, is positive 613.13. And if you use reduced row echelon form on that, you get a force vector R of 527.5, 210.2, and negative 35.1. What are the units for that? That's a force, so that's newtons. And then TA, we get a value of 429.6. That's a force, so newtons. And TB, we have 247.7 newtons. Is there anything we can use about the signs of these values to sanity check these answers? Like in general, there's not too much you can tell, but sometimes there are requirements on the signs of these things, remember? That's right, tension. That's the only thing that's useful here. Tension, a cable can't ever apply a pushing force, so those tension values always have to be positive. If you get a negative tension, that tells you need to go find a mistake somewhere in there. Okay, so the only thing we know is that the tensions look good. That gives us a little more confidence in the answer. Okay.
So tension has to be positive, right?
Always, yep. Any questions about that one? Are there people mention homework problems that you'd like me to do?
Number 10,
Number 10. Oh, I corrected a solution to number 9, by the way, so if you have that printed out again. Okay, number 10. Okay, number 10 is more cable. Does anybody want to see 13 or 15? Do them all? Let's do 13 first, because that has something that I wanted, that I want you to see.
15 as well, just because.
Yeah, sure. It doesn't have a solution? Oh, 13 does have a solution, but 15 doesn't? Okay. So, let's go through 13 first, so I can explain it. It's a little bit simpler thinking than 15. So this one, you have a support on this side that connects to this rigid contraption with like a handle going one way and a handle going the other way. Half of the difficulty of these 3D problems is just drawing the picture. And then this one's connected by a cable to the ground. And there are forces. There's a force back into the page of 750 newtons, and a force along the direction of the axis of 600 newtons. This distance is 200 millimeters. I'm going to just put all this stuff in meters right now. So 0.2 meters. Let me put the dimensions in something else. The height this way is 0.2 meters. The distance between these 2 points is 200. And then between here and here is 0.2 meters, and between here and here is 250 millimeters, 0.25 meters. And we want to figure out Okay, if we call this joint, no. So the way I'm going to do this is I'm going to just put the origin at the about point. Well, I guess that's getting ahead of myself. Let's do the free body diagram first. Oh, that's even getting ahead of myself because I need to tell you that, okay, this point is called A, and this point is called B. And it says that bearing A provides thrust. And not B. So the bearing at B doesn't provide thrust. And so a free body diagram so there's the outline. It doesn't give any weight, so we're neglecting the weight on this. There's a cable at the front here, so there's a force downward. I'll call that T. And then if we keep going around the boundary, we get over to the bearing B. That is that's a pin joint without thrust. So let's think about what that applies. So we know that this pin joint keeps this point on the rod from translating in a plane like this, right? It doesn't keep it from translating along the axis. That's what thrust would do. So it's going to apply a force component this way and a force component that way. I guess I'll call the x-axis along the axis of the rod, so then this would be R, B, Z, and this would be R, B, Y. Any questions about those, first of all? There's one more thing we have to think about with this.
Not necessarily a question on those.
Yeah.
But why is it that free body diagrams in 3D are still just the outline? Wouldn't it be simpler to just have the 3D object?
I do it just the outline because what you're really, the point of the free body diagram is to be very clear to yourself about where the boundary is between the object and the outside world. If you want to draw the 3D object, that probably is perfectly reasonable. I still do it like this, but I don't,
Okay.
yeah. I could see that argument for sure.
I just find most of the time when I'm working like this, I get confused, like,
Yeah.
where the dimensions
Yes.
are because it's a 2D object that's 3D.
Right, yes. Yes. Yeah, in 2D, I'm 100% set on the fact that it should just be an outline. In 3D, I do what you feel like a little more, yeah. I don't really have a strong feeling about it. Any questions about those forces, first of all? Because now we still have to think about the couples. So remember that if you look at the list of joints, a pin joint without thrust applies two force components like this. And it also provides possibly two couple components.
it never provides a couple about the axis because it doesn't prevent rotation, around the axis. That's what a pin joint is supposed to allow. But it can keep this thing. Imagine that this is only connected to this pin joint for a second. It can keep this object from tipping that way, and it can also keep it from coming out of the board. Those are the two couples it can provide. A couple, so the one preventing it from going down this way has an axis like this, and the one preventing it from coming out of the page that way has an axis like this. Okay, and that pin joint is capable of applying those couples, of preventing those rotations.
It does move like left and right, like.
That's right.
Yeah.
That's why there's no RBX component for the force.
Yeah, but the couple is like rotate either this way or rotate the other way like this way. Yeah, that's how we prevent it.
Yeah, so 2 rotations are prevented, 1 isn't. The one that isn't is just that thing spinning around the rod. Okay, but anytime you have 2 pin joints acting along the same axis like this, you leave the couples out. Okay, that's the rule. So in this case, just because we also have this pin joint at A, we're not going to apply the couples. Okay? Any questions about that?
That's only because it can't move.
That's right. It's because the rotations that would be prevented by those couples are prevented by the forces at A.
It doesn't prevent it to even move this way as the x-axis, but B it moves in the x-axis. So it's kind of different. Like they're connected. One of them moves, but how does it move?
Yes. So when you think about what motions are prevented, you have to think about. You don't think about the rest of what's going on. You only think about that joint. What if only that joint was there? Okay. So yeah, this. I mean, really, since this is statics, every motion is prevented. But the question is, what's prevented by that joint? Okay. And then we have these 2 forces here. 750 newtons there. 600 newtons there. And now we get over to the bearing at A. That prevents translation in this plane. So there's an RAZ, an RAY, and this one also provides thrust. So in this case, there's also an RAX. I guess I could have just written this as a vector RA, but
The thrust can be negative or positive.
yes. Yep. Any questions about that free body diagram? And now I said I was going to put the origin at the about point, just so that I didn't have to write out P and A in this long form of the table. Where do you want to put the about point? That's right. Yeah, put it at A because that's where you have the most unknown forces. That gets the most forces out of your moment equations. That's the benefit of it. It's not a big deal, but it simplifies things a little. So let's put the about point here. And so we'll think about the origin being there too. Okay, so first, if the coordinate system is at A, what are the coordinates where that force R is applied, where that force RA is applied? 0. The force vector is RAX, RAY, RAZ. And so the moment is 0. And that's the benefit of putting the about point where you have the most unknown forces, that moment is always 0 from those forces.
Can we, so like each line, can we label what force
Yeah.
that's coming from?
Yeah, so this is our A. Yeah, so now we'll go to T. And so to get to T, you go 0.2 in the positive x direction, and then let me draw the orientation of the coordinate system here. So this is our x-axis direction, y-axis direction, z-axis direction. So to get to this point, we're going 0.2 in the x direction, and then 0.2 in the z direction, nothing in the y direction. So the rho vector is 0.2, 0, 0.2. The force vector is 0. This is in the negative y direction, so 0, negative t, 0. So you get 0.2 t for the x component, 0 for the y component, and negative 0.2 t for the z component. And now we get up to the forces of 750 and 600.
Can we treat those as like one?
You can treat them as one, yeah, or you can break them up into two. Okay, so the coordinates where that's applied, you go 0.2 and then 0.25 in x, so 0.45 x, and then you go vertically 0.2 meters in the positive y direction, so that's 0.45, 0.20. Any questions about that? So 0.45, 0.20. And the force vector, we have 600 in the positive x direction and 750 in the negative z direction. So the x component of the moment is negative 150. The y component is, what's 0.45 times 750? So positive 337.5. And the z component is negative 120. And now the last force is RB. So the coordinates of B, in the x direction we have to go 0.2 plus 0.25 plus another 0.2. So that's 0.65. And we don't have to go anywhere in the y or z directions. So that's 0.6500. The forces are 0x, RBY, RBZ. So you get 0 for the x component, negative 0.65 RBZ for the y component, and positive 0.65 RBY for the z component.
So y RBZ for the y component and RBY for the z component. Is it like I was thinking?
Yeah.
Is it should be flipped like RBYs and RBZ after that?
Because you, if you think of that determinant way of doing the cross product,
Oh, okay, I think cross product. Okay.
yeah, it's the cross product, right? Any other questions about that, about these values? And so now we can go to Newton's second law. It says RAX, RAY, RAZ plus 0, negative T, 0. I'll put this one over in the constants. So 0, RBY, RBZ is equal to, if I'm moving this the other side of the equation, no, don't do that. I'm just going to add it in. And then the moment equation says 0 plus 0.2t, 0, negative 0.2t, plus negative 150, positive 337.5, negative 120, plus 0, negative 0.65 RBZ, plus 0.65 RBY is equal to zeros. And for variables, you have 1, 2, 3, 4, 5, 6. None of these equations are degenerate, so we have 6 equations for 6 variables. And I don't know, maybe I just won't write out the table and stuff, but or go through the matrix calculation. But from here, you're just using reduced row echelon form to solve for those variables. Yeah. Any questions about that one? Okay, so let's do number 15. Yes? No, we didn't. It wasn't given, I don't think. So if it's not given, that just means neglect it. So what's going on, like, whenever problems neglect mass, and they do it pretty often, it's just that the weight is insignificant compared to the other forces, and that's a pretty common thing in any kind of robotics or civil engineering things or whatever. The external loads being applied dwarf the weight, and so there's no point in in worrying about it. Okay. The gear here has a radius of 1.5 inches. And the little gear has a radius of 1/2 inch. And the dimensions this is 4 inches. This is 3 inches. 2 inches. And that's all we need. And then the forces, the external loads, there's a downward force there of 96 pounds. A horizontal force of 265 pounds. And then this isn't super clear from my drawing, but the idea here is if you go straight horizontally from this, from the center of this gear, there's a force of 192 pounds. And an upward force of 530 pounds.
What pounds? Oh, just pounds.
So, what kind of joint are it like? We have 2 joints, right? But you didn't say what type.
Right. Well, so they're pin joints. You don't know anything about thrust, which normally in a problem like that, that's something like, that's the first thing that pops into my head when I look at it too. But then if you look at the direction the forces are acting, there are no loads that would require thrust. You know, thrust prevents this thing from translating along those pins. And there aren't any force components in that direction. So if one of those had thrust, what you would get is that force is equal to 0 anyways.
Oh, okay.
So this can function perfectly fine without thrust. Okay.
But does it still move? Not if, like,
It's free to move. You're right that if it doesn't say anything about thrust, it's free to move back and forth. It's just there's no forces being applied that would make that happen.
oh, okay.
Another, excuse me, another funny thing about this problem is that neither of these two joints, these are pin joints, so they don't prevent any kind of rotation, right? And so if you have a non-zero moment about this axis, this thing's going to spin. And you don't have a zero moment. This moment of 1.5 inches times 265 is bigger than 0.5 times 530. And so this thing is going to spin. But it just turns out we're not going to worry about that dimension. We're going to worry about the dimensions where we do have loads. Okay? So that's going to be our approach to this problem. Okay, so free body diagram. That's the outline. We're not including the joints in our isolated body. We have these external loads, 96 pounds there, 265 there. Over here we have a force of 192 and an upward force of 530. Yeah, so yes, you can always do these problems in units of inches and pounds. A lot of times I just convert because I'm used to SI units, but then you have to convert at the beginning and convert back at the end if it asks for it in inches and pounds. Might as well just keep it in these units. And now we have to think about the loads applied by those joints. So at C, that's a pin joint without thrust. So it's going to apply a force that way and a force that way. A full, you can think of it as a full force vector in the plane perpendicular to that axis. So this is RCZ, and this is RCY.
Technically speaking, don't we not know that it doesn't provide thrust?
We don't know. It doesn't say anything about it. Yeah.
For like X, Y, and Z, why is Z going like this?
It was given in the problem.
Oh, okay.
So the problem was given. So it said the z-axis is this way, the y-axis is this way, and the x-axis is this way.
So just to be consistent with what you're saying about the different joint types, should we assume that there is a force?
The axial thrust.
Yeah.
Just assume if it doesn't say anything about it, leave it out.
Okay.
And if the problem can't be solved with it out, the problem isn't a well-posed problem.
Okay.
You know what I mean? And what about the couples? So these pin joints can provide those two couples. But we're dealing with these two axial pin joints, and so we're going to leave those off. Right. And over here at D, these are the same two force types. That's also a pin joint without thrust. So RDZ and RDY. The problem put the origin here. You can move the origin around with each rigid body you choose. You can put it wherever you want. So if you like that origin, keep it. It's a pretty good suggestion in this one, so we might as well keep it. But you're free to move it. And if we're going to make this the origin, let's also make that the about point. So Rho Force Moment. So I'll start with this force RC. That's at the origin, so the rho vector is 0. The force vector is 0, RCY, RCZ. And the moment is 0. And now let's go to where this 96 and 265 is applied. We can do that all at once. So the location is 4 inches in the positive x direction, and then 1.5 inches in the positive y direction. So the rho vector is positive 4, positive 1.5, 0. Any questions about that, the coordinates there?
Can we leave the meters and inches as it is?
Yes. You can, do it however you can convert it or leave it.
Well, like mixing the inches and the meters.
Where's meters? I think I just wrote it wrong.
Radius of the disc.
Oh, that's in inches too. Everything's in inches. Yeah, it looks like an M with an umlaut, but it's in inches. And the force vector up there is 265 in the positive z direction, 96 in the negative y direction. And so the cross product, what's 1.5 times 265?
397.5.
Okay, and then what's 4 times 265?
1060.
Okay, and then 4 times negative 96. I'll do the negative, you do the number. 384. Negative. Yes. And then the next force is at D. The coordinates of that point are 7 inches in the positive x direction, no y, no z. So 7, 0, 0. And the force is 0, RDY, RDZ. The x component is 0. The y component is negative 7 RDZ. And the z component is positive 7 RDY. And then the last one is the 192 and 530. This one was RD. So the x position is 9 in the positive x. There's no y. The z position is 0.5 in the positive z. So 9, 0, 0.5. And the forces are 530 in the positive y, 192 in the negative z. Oops. So 0, what did I say? 530, negative 192. So what's that, 265, negative 265x? For y, what's 9 times 192?
1728.
Okay, and then for z, what's 9 times 530? And that's everything. So Newton's second law says 0, RCY, RCZ, plus 0, negative 96, 265, plus 0, RDY, RDZ, plus 0, 530, negative 192. And the moment equation says 397.5, negative 1060, negative 384, plus 0, negative 7 RDZ, positive 7 RDY, plus negative 265, 1728, 4770. And I'm going to write this now as 0, 0, 0. But this problem is unusual because, like I said at the beginning, this one is not actually in static equilibrium. It's free to rotate about the axis. And you can see that if you look at this this x moment equation. That's the rotational equation related to rotations about the axis. And you can see that doesn't make any sense. There are no loads to counteract these moments. And so this is not really. But it doesn't matter to us because we're just not going to deal with that equation at all. That equation doesn't have any variables in it, so we're just.
It's all like numbers and
Yeah, exactly. Right. It doesn't make any sense, and the reason is that you'd get angular acceleration due to those non-zero moments, but we're not worried about that.
So that'd go into dynamics.
Yeah. Right.
We'd have a few variables again on the right side.
Exactly. Yep. Yeah, you'd get the moment of inertia times alpha, but we're just trying to calculate those loads, so it doesn't concern us at all. And so what you get is, and this one is obviously useless. And so what you get is 4 equations for 4 variables. and you can solve for those reaction loads. Any other questions about that one? Okay. If you bring questions on Thursday or Tuesday related to the test, I'd be happy to answer those. But basically, we're going to go on to the next topic when you're done with questions. Okay.